Nations Framework Convention on Climate Change, or UNFCCC, entered into force on 21st March 1994. They completed 25 years of existence a few days back, and during the anniversary, their executive secretary said that climate action is more urgent than ever. And this UNFCCC has a near universal membership now. The 197 countries that have ratified the convention are called the parties to the convention. Every country is a party to this convention. So it is called the COP. COP is the supreme decision-making body of this convention, and all decisions are made during the COP conferences. The most important COP conference recently was COP 21 at Paris in 2015. At this conference, the parties have announced their intended nationally determined contributions. That is, their intended nationally determined contribution means their intended climate action to fulfill the objectives of this Paris Agreement. That is to limit the increase in global average temperature to well below 2 degrees Celsius. India also made a few commitments. That is reduction of our emissions intensity by 33% by 2030 compared to its level in 2005. Plan to derive 40% of our electricity from renewable energy sources and create an additional carbon sink by through reforestation, that is increasing the forest cover. That is approximately 3 billion tons of carbon dioxide. Intergovernmental Panel on Climate Change, or IPCC, set up by the World Meteorological Organization and United Nations Environmental Program in 1988, is for assessing the science related to climate change. They regularly release assessment reports on the scientific basis of climate change, its future risks and consequences, and various options of mitigation and adaptations to the policy makers. And these are policy relevant but not policy prescriptive. That means it is all advisory. If a country wants to accept it, they can take it for their purpose. And this forms the basis for discussions and negotiations during the UNFCCC conferences. Kyoto Protocol, the text of Kyoto Protocol was adopted in 1997, and the protocol to the UNFCCC is an international treaty that sets binding obligations on industrialized countries to reduce emissions of greenhouse gases. And this protocol recognizes that developed countries are principally responsible for the current high levels of greenhouse gas emissions in the atmosphere as a result of more than 150 years of industrial activity, and places a heavier burden on developed nations. And this increase in carbon dioxide concentration is believed to be the major cause of such an increase in temperature at that time. There was a special report by IPCC released recently, few months back, that is global warming of 1.5 degrees Celsius. And the objective of this report was to examine whether we can still limit the global warming to 1.5 degrees Celsius, which is a very ambitious target. The report recognizes that we are already facing the consequences of 1 degree global warming, such as sea level rise, increase in the occurrence of frequency of occurrence of extreme events, and shrinking of Arctic ice, sea ice, like so many other consequences. And they recognize that global warming likely to reach 1.5 degrees Celsius 2030 and 2052 if it continues to increase at the current rate. And they also recognized that climate-related risks to health, livelihoods, food security, water supply, human security, and economic growth are projected to increase with the global warming of 1.5 degrees Celsius and increase further with the 2 degree Celsius. And their recommendation is that theoretically it is possible to limit the global warming to 1.5 degrees Celsius, but rapid actions are needed and global cooperation is very much essential. And we have to reduce the anthropogenic or human-caused carbon dioxide emissions to 45% by 2030. That is from 11 years from now. It's a very difficult task. In all these negotiations and international policy discussions, the main focus is warming due to greenhouse gases. But there is another species in the atmosphere, atmospheric aerosols, which is very important in all these discussions. These are not gases, these are particles of solid or liquid phase suspended in the atmosphere. And they constitute only a small fraction of the atmospheric mass, but they have the ability to alter radiation. Whether it is incoming sunlight or outgoing long-wave radiation, they can affect the radiation. Typical size of an aerosol particle is 0.5 micrometer, making it radiatively very active in the visible region according to scattering theory. When the scatterer size is comparable to the wavelength of radiation, its scattering effect is maximum. Typical lifetime of these particles is about several weeks to months. Depends on the type of aerosol, and they can be of natural or anthropogenic or man-made origin. Soil dust, sea salt, volcanic dust, these are all part of natural aerosol system. And industrial sulfate, black carbon or soot, they are part of the anthropogenic aerosol system. The radiative properties depends on the chemical composition, which determines the refractive index of the species. For example, sea salt is a scattering type and it can scatter light back to space and leading to cooling of the planet. But at the same time, black carbon is an absorbing species, so it can absorb radiation and lead to warming of the atmosphere. So this is the simplest way I can explain what is the difference between light scattering and light absorbing aerosols. Light scattering aerosols in the left, it can scatter radiation back to space and it can also reduce the surface reaching solar radiation. But the amount is equal because there is no absorption in the atmosphere, atmospheric absorption is zero. So this is equal to reduced at the surface. So the warming is also zero. So they are cooling agents and partly offset the global warming due to greenhouse gases. But in case of absorbing aerosols, they can absorb radiation, so their surface effect is much larger than the effect at the top of the atmosphere, even though they radiate part of the radiation back to space. Because of the atmospheric absorption, they can warm the lower atmosphere. So they complement it to carbon dioxide. That is the reason I said atmospheric aerosols are also important when we talk about warming of the atmosphere. And if the particles are very large, the absorbing species or light absorbing particles are very large, we have to also account the long wave radiation, that is infrared radiation coming from the Earth's surface. So this is simply Stefan's Boltzmann law. When you have a surface temperature of T sigma T raised to 4 into epsilon, that is emissivity of the surface will be what going back to space. And whatever is emitted by the surface and whatever is reaching the top of the atmosphere radiation will be less because these particles can trap part of the energy in the atmosphere. And there are several reasons why aerosols are important. I will be talking about climate mainly, but aerosols are important because it can affect radiation. And because of that, it can affect climate directly by scattering incoming sunlight back to space and also absorbing sunlight. And indirectly, aerosol can act as cloud condensation nuclei and thereby modifying the properties and lifetime of clouds. And remote sensing, that is satellite remote sensing, it is important because it is acting as a layer in between satellite and Earth surface. So any remote sensing of the Earth surface like land use, land cover changes or sea surface temperature, we needed to correct for the aerosol effect before we get a reasonable data. And agriculture, it is important because of two reasons. It can affect surface reaching solar radiation, so the photosynthetically active radiation available for the plants will be less, and also it can deposit on the leaf, it can have some consequence. And in 2014, the World Health Organization classified suspended particulate matter as carcinogen. So that is its effect on health. It's all complex things, but I will be focusing on the climate impacts. During early to mid 1990s, the climate science community was focused on light scattering aerosol, as all of us believed that aerosol cooled the planet. For example, this is an observatory set up by IISER Geosphere Biosphere program. It is in the island Minikoi of Lakshadweep group in the India Meteorological Department office, and this was mainly to study the sea salt aerosol generated due to sea surface winds, and also for the transport of mineral dust from West Asia to oceanic region adjacent to Indian region. Indian Ocean experiment or INDOX was conducted during 1996 to 1999 to study the aerosol over tropical Indian Ocean. During INDOX, we have developed for the first time an Indian Ocean aerosol model, which when we incorporate in radiative transfer models could successfully explain the surface measured radiative fluxes. So this was the first time an aerosol model was developed over this region, and we also have demonstrated that this black portion is black carbon. We have shown that even though black carbon or this light absorbing aerosol species contribute only 6% in terms of aerosol mass, it can contribute 11% into aerosol optical depth and 35% into the radiating impact. Aerosol optical depth is simply a measure of aerosol concentration in the atmospheric column, and mathematically it is expressed following Lambert-Beer law in optics. So in simple terms, we can say that if aerosol optical depth is more, its aerosol concentration is more. And a series of experiments conducted during Indian Ocean experiment brought to light the importance of light absorbing aerosol, specifically black carbon aerosol. And we also had radiation budget measurements from the surface and also at the top of the atmosphere using satellites. And we have demonstrated that the aerosol induced radiative impact at the surface is 3 times larger than that at the top of the atmosphere. That means black carbon can exert intense warming of the lower atmosphere. And that was one of the first observations, and we provided an experimental evidence. And since then, black carbon aerosols received enormous attention of the international climate science community. And also, this INDOX experiment was a major boost to Indian aerosol science as well. These are the major inferences from Indian Ocean experiment. The first one is that black carbon aerosol cause cooling of the Earth's surface simultaneous with the warming of the lower atmosphere. And second is black carbon aerosol can affect natural hydrological cycle, and intense warming of the lower atmosphere due to black carbon aerosol can reduce cloud cover. That was an important observation. And you can see that it received wide attention from the media and the high impact journals. There were perspectives and news items published in Nature and Science journals. And this was the most important result, is that sooty air sweeps away clouds. And this absorbing phenomena or these microscopic particles, popularly known later as atmospheric brown clouds. There was a major project by United Nations Environmental Program on atmospheric brown clouds to study the light absorbing aerosols over South and East Asia soon after Indo-X. There were international policy implications as well. The most important one is that during early 2000s, some developed nations named exclusion of black carbon from the Kyoto Protocol as one of the reasons for their withdrawal from the agreement. So these nations wanted black carbon to be included in climate change negotiations, but since it was not, they have withdrawn from Kyoto Protocol. And the reason is the developing world, especially India and China, accounts for the largest volume of black carbon emissions. And India particularly is important in this discussion because of its close proximity to the Himalayas and the presence of high levels of black carbon emissions from the Indo-Gangetic plains. It may have an effect on glacier melting. These inferences had an impact, even though gradually, on IPCC as well. This is the fourth IPCC assessment report released in 2007. Its work started, the authors started writing the report in 2004. The chapter 2 is changes in atmospheric constituents and radiative forcing. So aerosol is only a small part of this chapter. And in chapter 7 in 2013, the work started in 2010. Clouds and aerosols. So there was a chapter specifically for aerosols. And in now, which is the report, the sixth assessment report is going to be released in 2021. Chapter 6 is short-lived climate forces. The three key short-lived climate forces are black carbon, methane and HFCs. So black carbon is getting much more attention in IPCC reports than before. And as I said before, the black carbon aerosol got enormous attention of the climate science community, but unfortunate fact is that the inferences by different groups across the globe also shows contrasting inferences. When one group says aerosol reduce monsoon rainfall, another group says aerosol intensify monsoon rainfall. Like that, large number of inferences are contrasting. It's obvious because they use different models, different parameterization, different input data set. We know that even if you use the same input to two different models, we get different output because of grids, rough solution, parameterization and so many other reasons. And occasionally simulations in some studies appear closer to reality but due to wrong reasons. It is not because they are inputting correct aerosol properties. Adding to this complexity, optical properties of black carbon aerosol from different sources, for example, vehicular emissions, biomass burning and so on, are also different. We don't have a standard aerosol model for one region or other. In India, aerosol research started in 1984. As part of Indian Middle Atmosphere Program, a project was initiated to monitor aerosol properties at different locations in India. And as I said, Indo-X was a major boost for Indian aerosol science. There was only 6 stations in 2000 and 41 in 2010. So soon after Indo-X, the number of stations also have gone up. And if we use the data from RFNet, we can see that until 90s, there was a 1.7 per year increase in the aerosol over India. And during the last decade, specifically after 2000, the rate of increase is 2.3% per year. And if this rate continues unabated, aerosol optical depth, which is a measure of aerosol concentration, is going to reach unity, that is 1, which lead to exponential decrease in the direct surface reaching solar radiation, according to Lambert theory. No, it is direct radiation. So there will be diffuse radiation. Yeah, by 2050. And if the rate of increase continues like this, it's increasing as of now. During early 2000s, question we have been trying to address was whether aerosol microphysics and chemistry explain the radiation budget. We can measure the radiation and calculate the radiative impact, and we also can simulate using radiative transfer models by incorporating measured aerosol properties into the model. We see large discrepancies between the two, nearly doubled, and this means that we are missing something serious in our model, or some energy is missing in the model, or atmosphere absorbs much more than predicted by these models. And we also noted that discrepancies are significant whenever there is an aerosol layer above. This is observation from micropulse data where we can send a laser pulse and get the vertical profiles of aerosol. And this has led to several hypotheses. The most popular one is gas X hypothesis. That means an unidentified absorber may be present in the atmosphere with similar optical properties as that of black hole. So we have tested so many options. One is gas X, another one is artificially multiplying DC by 4 by a factor, but we found that we have to multiply as much as a factor of 4 to get agreement between model and observation. And we also examined the state of mixing, how these aerosols are mixed, whether they are mixed internally or externally, they are existing independently or they are attached to each other. A series of field campaigns and investigations during 2005-2006, we have synthesized the data from all these campaigns, and we have provided the observational evidence to show that this highly debated anomalous absorption is partly due to the unrealistic description of aerosol state of mixing. We can explain this missing energy by incorporating proper state of mixing in the models, but not completely. And this partly solved the issue, but it has raised another question: how representative are the aerosol impact assessment? So the conclusion is that aerosol radiative impact assessment by assuming black carbon as an independent species are unrealistic. That means all the past estimates are unrealistic. In 2007, IPCC released the assessment report 4, and they have made a very controversial statement that glaciers in the Himalayas are receding faster than in any other part of the world, and if the present rate continues, the likelihood of them disappearing by the year 2035 and perhaps sooner is very high. So this has got again the attention of the media, and some of the newspapers said that 90% of Himalayan glacier melting is caused by black carbon. So it has become a habit that any environmental phenomena just attributed to black carbon, that become a kind of habit. And it has raised several questions. Vertical distribution of aerosol, we didn't have enough information on the vertical distribution because most of the aerosol sources are close to the surface of the earth. So we did not think that it can go up through various mechanisms. And another question is, what fraction of surface aerosol can reach glacial altitude? That is also important in this question. So we have two issues here. One is anomalous absorption, where we are missing some energy in our calculations. And another one is their potential impact of this light absorbing aerosol on deposition of glaciers and consequent impact on the glacier melting. So to study the vertical distribution of aerosols, we have conducted a series of campaigns known as integrated campaign for aerosol gases and radiation budget. It was an extensive multi-institutional and multi-platform field experiment carried out over continental India and adjacent ocean. And major objective of this campaign, the biggest campaign ever conducted over the Indian landmass, was to characterize vertical distribution of aerosol and assess its radiative impact over Indian landmass. And a network of ground-based observatories over the mainland and islands, a dedicated ship, Sagar Kanya of Ministry of Earth Science, instrumented aircraft of Indian Space Research Organization, formed the 3 segments of this integrated campaign. This was conducted from 2006 to 2016. These are some of the aircraft tracks we have flown. And this is the ISRO's aircraft which we have used. And in addition to this, we have also used the aircraft from UK, that is Facility for Airborne Atmospheric Measurements, FAAM. The series of experiments conducted as part of ICAR provided us valuable information about the elevated aerosol over India, and we found that most of the aerosols are located between 3 to 4 kilometers, not close to the surface as we expected, because most of the sources are close to the surface. In fact, all of the sources are close to the surface. We expected that large amount of aerosol will be close to the surface, but in this case it is at an altitude. And we also found that when we tried to simulate the vertical distribution using models, that is radiation models, we found the discrepancies are huge after above 2 kilometer altitude. And there are 2 questions here. What causes the formation of elevated aerosol layer? What is making it to hang like this in the air? And what causes these large discrepancies at higher atmospheric levels? This one. Yeah, this is red is more, blue is less. This is horizontal gradients from the land when you go to ocean. Bhubaneswar, Chennai and Trivandrum, when you go to the ocean, you have a decrease in the kind of exponential decrease in the aerosol concentration. So we had radiosols profile, and our radiosol profiles have shown that 2 convectively unstable layers, one from the surface to about 1.7 kilometers and another one from about surface to about 1 kilometer and another one from 1.7 to 3 kilometers, and a convectively stable layer sandwiched between these 2 unstable layers. So our model studies have shown that these convectively stable layers can act as conduits for keeping or trapping these aerosols and favor long range transport without letting them entering into the boundary layer, atmospheric boundary layer below. So this is what is causing the layers, formation of layers. It is trapping of aerosol at 2 to 3 kilometer altitude. It doesn't apply because it is trapped between 2 layers. We also have observed that if you go from northern Indian Ocean to central India and northern part of India, our layer height, there is aerosol layer, mixed layer at which the aerosol is concentrated increases with the height. And this cloud, symbol of cloud is representing the approximate altitude of clouds, and it is showing that more than 70% of the aerosols are above clouds in central India compared to about 10% over northern Indian Ocean. There is a reason why it is below or above clouds. I will tell you in a few minutes later. And we did not have the observations throughout the year or throughout the season, so we had to depend on spaceborne LiDAR, that is Calypso of NASA and the CNES of France. And we have clearly seen this kind of meridional gradients of layer height in Calypso data as well. You can see that this is Himalayas, and close to the Himalayas there is an accumulation of aerosol up to an altitude of about 4 kilometers, and when you come to the southern part of India, it's very close to the surface of the earth. And we still needed to study what causes or what is the composition of that elevated layer. So one way to do that is study the microscopic features so that we can incorporate them in radiation models. So we have done scanning electron microscope images, and the purpose was to find what fraction of the black carbon is contaminating other aerosols. So here we have used an image processing technique by mapping image pixel intensity ratio values retrieved from energy dispersive spectroscopy, and we have plotted this. We found that 61% of the area of the core is covered with an identifiable shell, and that is mostly black aerosols. And the entire shell area, 47% is composed of carbon and 53% is composed of dust. And the reason why we are examining this kind of core shell structure is that it is well known that when particles are contaminating other particles, like in the form of a core shell, its optical effects can be much larger compared to the case when they are existing independently. So the inference here is that it's very complicated, but the inference here is large dust aerosols are contaminated with the black carbon and partly fine dust. That means such mixed aerosols having radiative effects much larger than expected. So this is the summary of all our campaign observations for several years, and you can see that 10 to 20% of aerosol over South India and Indian Ocean, they are above clouds, and about 50 to 70% is above clouds in case of North and Central Indian region. And why it is below clouds and above clouds, I am saying when the aerosols are below clouds, most of the radiation is blocked by the clouds. So it is not directly interacting with the thing. So even if it is a light absorbing aerosol here, the interaction is very less. But here, since the aerosols are located above clouds, clouds can act like a mirror. It is a highly reflecting surface. So most of the radiation is going back and interacting with the aerosol, and its warming effect, especially when it is contaminated with touch, that means it is in mixed state, it will be much more. So this can cause a warming of 2 to 4 Kelvin in this region, that is North and Central India, and about 0.5 to 1 Kelvin over the South India and Indian Ocean. So that means there is a strong aerosol induced north-south temperature gradient at 4 kilometers, and typically it is about 3 Kelvin, or in extreme cases it is about 6 Kelvin. And if we incorporate this scenario in radiation models, which was never done in the past, we see that intense warming due to absorbing aerosol above clouds in northern part of India is capable of triggering dry convection. It heats the atmosphere and it can trigger dry convection and force the air from southern part of India towards north. So because of this 3 to 6 degree Kelvin temperature, meridional temperature gradient. So this air is moist and this air is dry because it is coming from the ocean. And as I mentioned, all the inferences about aerosol climate impact, even though there was an increased interest in the influence of aerosol on climate, most of the studies have either used the output from chemistry transport model or satellite data, because it is very easy to get. Most of the studies, if not all, have not used measured observation, aerosol observation from Indian region in any of the models in the past. So this is one example. We incorporate directly measured aerosol properties into the model, and we see that moist air from the southern part of India can move towards central and north India. And this is the outcome if you use this scenario in a climate model. This is output from a weather research forecast model. We see that there will be enhanced rainfall over the northeast region and some part of central India, and there will be a reduction of rainfall over the southern India. And aerosol heating induced north to south migration of rain band. Rain band can move from south to northeast, and there will be a lot of effect on winds also. Just before the release of IPCC report, assessment report 5, that is 2013, around 2012 to 2013 period, there were some reports which project that black carbon radiative impact is 2 to 3 times larger than we thought. A fraction of the scientific community, including some of us, felt that evidences presented are not adequate to substantiate their conclusions. So you can see the news item associated with these reports. say that black carbon and warming, it is worse than you thought, and black carbon a powerful climate pollutant. Similar large number of news items have appeared around this time, and all these statements have enormous implications to international policy on climate change. So we have looked our data, our own data, that is RFNet data over Indian region. This is the black carbon data from RFNet, and color bar indicates black carbon in microgram per meter cube of air. And we can see that there is a decreasing trend in black carbon, not an increasing trend. So there is a question of multiplying the existing numbers to 2 to 3. So it is decreasing actually, and even if you take all India average from 2006 to 2016, last 10 years there is a decrease of 10 due to various emission control measures by government and due to various reasons. So the only standard deviation. So we have a strange situation here. I have shown you before an increasing trend in aerosol, that is atmospheric column, and now I am showing a decreasing aerosol trend of black carbon aerosol at the surface. It looks contradictory, but it is not, because if there is a growing emission at higher atmospheric level, then this can happen. If you can have an increasing trend in atmospheric column, but there will be a decreasing trend in the surface aerosol concentration. That is possible. So we have examined that aspect. This is data from Calypso spaceborne radar. We have seen that there is an increasing trend in the contribution of the atmosphere above boundary layer to the column aerosol oxidator. So the only way to study this is using high altitude balloons, by sending sensors in high altitude balloons, and the only facility we have is TIFR facility in Hyderabad, and they have this 109K cubic meter balloon which we can send up to sensors up to 35 kilometers. So this is the facility we have used, and this is we are filling hydrogen in the balloon, and this is just to show that how big the balloon is compared to the people around. And this is the launch. We can send the instruments in this balloon up to 35 kilometers, and there is a parachute here. After it reach about 30 kilometers, they can send a telecommand to blast the balloon, and they can retrieve the instrument back. The instrument will come back in this parachute, and we can retrieve it from about 30-40 kilometers away from the launch sites. So this is a longer video, so I will stop there and go to the next slide. So this is the result we have got from this balloon flight. After 9 kilometers we couldn't take the data because the pump failed after 9 to 10 kilometers, because our pumps are not strong enough to suck air from such a small, such a thin atmosphere at that altitude. But the most striking feature we have found from our measurement is that huge amount of black carbon between 80 to 9 kilometer altitude. This is comparable to that we see usually in Bangalore or any other metro cities. 4 to 6 microgram per meter cube of black carbon at around 9 kilometers is huge values. It will have huge implications, I will tell you in few minutes. So what is the reason for this? We didn't know at that time. So we have continued our investigation to find the source of such large aerosols at that altitude. One way we can do it is using models. This is the weather research forecast chemistry model. This is an online chemistry transport model. We have used several models, but this is one among them. We can simulate aerosols and clouds in this particular model. So we have considered several possible mechanisms and sources. One is vertical lofting of aerosol from the surface, local confinement by convectively stable layers, as I mentioned earlier. long range transport of aerosols from other locations and other local sources. And we have used the MAXITI global anthropogenic emission inventory. The reason is it has aircraft emission, because we considered the other three possibilities. It was not possible to simulate that peak what we have observed here. But this particular model we can also prescribe aircraft emission, because that is considered as one of the sources at this altitude, because this is the altitude at which aircrafts are flying. And the basic information this global inventory considers are the global aircraft movements, performance of various aircraft types, actual parts of aircraft, BC emission factor. And it has of course inherent uncertainties as well, mainly due to this BC emission factor, because BC emission factor is BC black carbon emission per kilogram of aviation fuel burned. And that depends, their uncertainties associated with uncertainties in total aviation fuel used, quality of aviation fuel, age of aircraft and degradation in the performance, exact number of civil aircraft, unaccounted military aircraft. But for a qualitative analysis, even though we will not be able to reproduce these results quantitatively, for a qualitative analysis, this was adequate. And we have tried so many balloon profiles in this model, and when we use this model with emissions from surface of the earth only, there is no indication of any layer in that level. But we prescribe aircraft emission in this model. It can clearly reproduce, even though the exact altitude is not the same, but it can reproduce this layer at this level. And this was repeated for several profiles, and the red is surface plus aircraft emissions and the blue is surface emission only. You can see that whenever we prescribe aircraft emission, you can reproduce that peak at 10 kilometers, and which is a clear indication that the source of that particular peak is coming from aircraft. And to make sure that there is no contribution from the surface, we have switched off the surface emissions and run the model again, and you can see that this blue and red are overlapping each other here. There is no effect of surface at all in the formation of these layers. So this clearly indicates that aircrafts are having a clear role in formation of that layers, and this is a small short video I have downloaded from YouTube, uploaded by Zurich School of Applied Sciences in 2010, and you can see this is the air traffic across the globe, and you can see this is London Heathrow to New York route. It is the busiest route in the world, and even over Indian region large number of aircrafts are flying, and there the illuminated region is daytime, dark region is night, and you can see for the 24 hours period how the air traffic is changing. So the summary from this kind of image is that a blanket of black carbon aerosol is present at around 10 to 12 kilometer level, sustained due to the continuous emission from high flying aircraft. It cannot sustain at that level, there is no stable layer at that level, but if it is a sustained emission like this, see the density over United States and Europe, if it is sustained emission like this, it can sustain a layer, and we have confirmed it again with the Calypso spaceborne LiDAR data. This is over Atlantic Ocean where this London Heathrow New York route is there. You can see the layer at that level, 12 to 14 kilometers where these high flying aircrafts are usually flown, and definitely the lower boundary layer profile, the peak is also there. This is average of 55,000 profiles. And anywhere in the ocean, remote location, or anywhere in the world you take, Calypso shows this peak. That clearly shows that this peak is coming from aircraft emissions. And why we worry about that peak? Because if there is a large concentration of black carbon at 10 kilometers and we are all living close to the surface of the earth, we should not be worried about that. But the issue is that if this particle can go up to the stratospheric altitudes, then their climate impact will be much more. I will tell you in a few minutes. And this is one mechanism, it is called self-lofting
because the BC is highly absorbing, it can heat the ambient atmospheric layer where it is located. And this will not happen close to the surface because density of the atmosphere is so thick close to the surface, and a small amount of absorption cannot lead it to convection. That is not easy. But at 10 km here, the aircrafts are already injecting large amount of light absorbing aerosol at this level. Here, a small amount of absorption can lead it to, because the atmospheric thickness, the thickness of the atmosphere is so small. So it can cause dry convection and take the particles to higher level, and again that heat to that level, and it can go up to even to higher levels. So in that way it can go up to 18 kilometers very easily. And one group from Europe, they have used forward trajectory analysis to track smoke plumes from Australian bushfires, and they found that they are actually following this step by step. They call it a solar escalator, and in a matter of few days it can go up to the 18 kilometer. Why 18 kilometer? Because there is a tropopause layer is at around 18 kilometer altitude. It cannot, the vertical transport is not favorable because of the temperature inversion at that layer. It is a border between troposphere and stratosphere. So the question is whether this particle can reach stratospheric altitudes, because it can reach up to tropospheric top of the troposphere, that is tropopause, but whether it can penetrate or not, that was the question which was bothering us. This is an old study which I found, the oldest probably in the literature. Professor Paul Crutzen, who got Nobel Prize in 1995, he said in some of his papers during late 80s that the consequence of nuclear war. So what will happen if there is a nuclear war? How the particles and smoke from such an event episode will affect the climate. So gaining inspiration from this, a group of researchers from University of Washington, Seattle, they have used this fire research facility at Tyndall Air Force Base in Florida, and they have conducted so many fire episodes using aviation fuel. And they found that it can lead to strongly absorbing, light absorbing aerosols such as black carbon, which can cause intense warming of the atmosphere. Why it is not going up? Because of the boundary layer. TBL is planetary boundary layer. Again there is a temperature inversion just like that tropopause. We have a tropopause, so it's blocked here. So even at the tropopause altitude, the aerosol, even if it reach 18 kilometer altitude, it will be blocked like this. But they have shown that in a matter of hours, the strong absorption and consequent solar heating of this optically thick aviation smoke, it can trigger dry convection, and it can cause the smoke to be lofted above the temperature inversion in a few hours. And if this can happen in a dense atmosphere close to the surface, it can easily happen in tropopause altitude also, because the atmosphere is so thin. A small amount of absorption is sufficient to create a strong warming, and the particles can go up. So the summary is that aviation smoke can penetrate the boundary layer temperature, and also there is a possibility that it can go and penetrate the tropopause altitude. Again, we have conducted some model simulation. This is the output of our model simulation using WRF-Chem model, and surface and elevated emission both are prescribed here, but we don't see that it is going above 18 kilometers here. And we also conducted runs using only aircraft emissions. Still at the most it can go up to 15-16 kilometers. One reason is because of color bar, it can go slightly more, but not above 18 kilometers. So there are no evidence that particle can go above tropopause level, that is reaching stratospheric altitudes. But again we have this Calypso data on stratospheric aerosol extinction coefficient. This is from 20 to 30 kilometers. And you can see that some particles are present at that level. and the extinction coefficient is 0.4 to 0.6, around 0.2 to 0.4 in all cases. This is Indian region. I can tell you that 0.04 extinction coefficient is equivalent to 10,000 black carbon particles per meter cube, per centimeter cube. That is quite huge actually. So it is showing, what it is showing is that there are black carbon particles, and we can also use with the help of depolarization ratio, because it shows the non-sphericity. We can distinguish between dust particles and black carbon. So with this values we can clearly say that these are all black carbon particles, and even over remote region of Atlantic Ocean you can see large amount of black carbon particles, and there is no difference between Indian region or Atlantic region. So throughout most of the locations we can see this kind of values, that is from 0.0 to 0.04. That means substantial amount of black carbon is present in the stratospheric altitudes. This is not adequate. I can tell you that this is only indication. If Calypso is there, why you need to do experiments? Because we don't have detailed information. This is only indication. Extinction coefficient only say that we have some particles, but we don't know the optical or physical or chemistry of that particular region. So this is only an indication. So it is indicating that yes, particles are there, and there are some more evidences that aerosol can reach stratospheric altitude. There is an increasing trend in stratospheric aerosol optical, that is average of 20 to 30 kilometers from 2000 to 2014. There are some publications which say that 4 to 7% increase in aerosol per year at altitude range of 20 to 30 kilometers since 2000. And another study say that there is a systematic increase in stratospheric aerosol has been reported by these people. So this shows that whether from the surface, this is a column integrated value of aerosol, but whether from the surface or aircraft, there is an increase in trend in aerosol in the stratospheric altitude. So why we worry about aerosol in the stratosphere, especially black carbon? The reason is several studies have shown in the laboratory loss of ozone on black carbon aerosol, and they also have shown that rate of reaction has a positive temperature dependence. Since the atmosphere is dense close to the surface and very thin at higher levels, for a given absorbed energy, consequent warming is substantially larger in high atmospheric levels. For example, for the same aerosol which can cause 0.3 to 1 Kelvin per day warming, it can cause 5 to 10 Kelvin per day at 20 kilometers at stratospheric altitudes. So there are several other work it is available in the literature about stratospheric warming due to the presence, in case there is a black carbon present, because stratospheric geoengineering is a proposal artificially modifying the atmosphere to cool the planet. So they all said that it can lead to intense stratospheric warming if black carbon is present in the stratospheric altitude, and global ozone loss up to 50% and so many other risks. And in addition to ozone depletion, there can be regional drought, and several people said it is a cure worse than the disease. So whatever reason, this is a different issue. It is stratospheric geoengineering where we artificially inject particles in the stratosphere, and this is another case which I am presenting is a natural. Natural means human made aerosol going to the stratospheric altitudes through several mechanisms. And this is some other reports about BC ozone chemistry from the literature, but all the reports are saying that if present, it can act as, it can provide a neutral surface area for chemical reaction which can deplete ozone. So understanding BC ozone chemistry is particularly important in the light of above observations. It is not completely known, and so far we have been worrying about the effect of climate change on aviation, that is reduced the lift, extreme weather condition and delay of aircraft, and increased the frequency of cyclone. And in Cochin airport was closed due to extreme precipitation in August 2018, and typhoon Jebi in Kyoto that has led to the closure of Osaka airport for several weeks and months. And now effect of airplane emissions on climate. But are we in a position to make a conclusive statement regarding the role of BC aerosol on stratospheric aerosol ozone? I would say no, because all these studies which I have shown available in the literature were conducted in laboratories and were not performed under the same conditions as found in the upper troposphere, lower stratospheric region, that is BPLS. And reaction probabilities that were determined under typical laboratory condition may differ substantially from reaction probabilities under real atmospheric conditions existing at stratospheric level. And finally, only a small fraction of aerosol may reach stratospheric level. We do not know. So it is important to quantify the amount of aerosol crossing the UTLS region for an accurate assessment of its role on ozone depletion. And before I close, this is some of the inferences and recommendations which we have found from our studies and campaigns. Definitely it is dangerous to have black carbon aerosols in the stratosphere, and amount of black carbon which can reach the stratosphere is still an open question which needs to be assessed. And aerosol ozone heterogeneous reactions are more complex than integrated approach involving in situ measurements at stratospheric levels using aircraft based high altitude balloon borne experiments along with multi-satellite data analysis and three-dimensional models. So I am working on this for the last 25 years, and these are the summary and inferences which I can say is not conclusive. The first one is climate impact assessment of light absorbing aerosol like black carbon aerosol remain a mystery, mainly because several climate relevant aerosol parameters are still unknown or uncertain, especially over South Asian region. And this elevated absorbing aerosol, since we do not know the exact state of mixing and the properties of this elevated absorbing aerosol, partly because of lack of data, and this happens often during summer and pre-monsoon season, makes aerosol monsoon studies a challenging task. And the strong meridional gradients in aerosol-induced warming can alter the atmospheric circulations and spatial distribution of monsoon rainfall. That is again an indication, no conclusive results on that yet. And there are three processes according to our observation are responsible for the presence of substantial amount of black carbon aerosol in the upper tropospheric, lower stratospheric region. One is black carbon from the surface sources carried aloft by the strong monsoonal circulations, and second is following the self-lofting mechanism where black carbon can go to higher levels due to strong absorption, warming, convection cycles. And third is aircraft emissions and subsequent uplifting by self-lofting process. And aircraft emission is not accounted anywhere. I hope IPCC assessment report 6, which is going to be released in 2021, will include aircraft emissions and its consequent impact, including the possible stratospheric ozone loss, which will be a global catastrophe. And I believe it is more questions than answers. One is, there are several questions which are not unanswered. One is, can light absorbing aerosol affect Asian monsoon? There is no conclusive answer. And impact on tropical cyclones, whether it will intensify or weaken tropical cyclones, there is no clear answer. And what fraction of tropospheric aerosol can reach stratospheric heights, and can aerosol destroy stratospheric ozone, and if present in the stratospheric heights, can black carbon can delay the expected discovery of the ozone hole, and so many. So in summary, in my opinion, crucial questions to be answered to understand the climate impact of light absorbing aerosols are so many compared to what is known today. And thank you very much for your kind attention. I thank once again IISER for organizing this lecture. And Infosys Science Foundation for presenting this prestigious prize to me. Thanks to mentors, colleagues, collaborators, postdocs, graduate students, project and office staff members. Without them, this would not have been possible. Thank you.